Hi, and welcome to the Austin Chemistry Laboratory here at Brigham Young University. My name is Matthew Miles, and I'll be presenting with my colleagues Jonathan Pershing and Noah Durst on proportional only control. This is a senior level class at Brigham Young University. We've been taking from John D. Hedegren. We'll be walking you today through our implementation on a proportional only control on the system behind me. We are Our goal was to ramp a cylinder of aluminum at a constant temperature rate in order to separate atoms from the walls of this contraption so that we could send them through a mass spectrometer and get valid readings from it. My colleague Noah Durst will walk us through our simulation or our physical model.
Hello, everyone. That's me, Noah Durst, and I will indeed take you through the physical model. So here it is in its entirety. Most importantly, we have the microcontroller, which takes input from a thermocouple going to a cold junction module. Then we have the servo hooked up to a variable transformer, which is then attached to heating wire that outputs heat into our system. As you can see, we have it running right now, and the servo is responding to inputs from the thermometer, and it is tracking to the set point temperature that is on a constant ramp. Matthew Miles will go over what facilitates this process for us.
Yes, thank you, Noah. As you can see here in our slides that we are pulling up, there's three simple items in a proportional only control that are needed. First is a sensor, which was our MAX 6675, our actuator, which was a servo connected to a variable transformer, and finally our controller, which we used an ESP32.
Thanks, Matthew. We were actually very surprised at how well this P-only controller performed from the get-go. We started tuning this P-only controller with a proportional gain constant based off of our approximations from our first principles model. It gave us a proportional gain constant of about 10, and we gradually increased this to see if we could reduce the offset, as you can see in this first figure. Increasing it to 20 and then to 30, and then finally to 40, it appeared that we reached the cutoff of offset reduction, and we began to saturate our variable transformer output, heating output, which wasn't great. So we ultimately decided that a gain constant of 30 to tune this controller would be the most effective for our application. This controller tuning appears effective because it produces the constant ramp rate. As you can see, it follows the set point very well. It avoids maxing out our variable transformer output and keeps it within reasonable servo angles. It minimizes offset and created an awesome P-only controller for us. So we're very pleased with the performance of our P-only controller, but lots of work remains to get it to function properly with the evolved gas analysis chamber behind us. First off, we are planning to incorporate a higher resolution stepper motor, which will provide a more precise actuator performance to within 0.7 degree increments. We also want to upgrade the assembly. We want to 3D print parts so that it's more permanent and it reduces safety incidents, error, noise. And finally, we need to ultimately fit this entire apparatus within the vacuum chambers behind us. It needs to function at extreme temperatures. So we think we're very close. This was a huge milestone for us, and our P-only controller is the best. Thanks so much for listening.
It's actually not true that